There we are. So we've got A colliding into B at a rate of 5, and then A and B. I was hoping for a second quick way actually type something out. I'd like as many viewers as I have, varying treat, and I don't like bots, so no, thank you. We've got the equal and opposite reaction. So that's important context. And the visual design principle of negative space. So you see in this little illustration, I've colored in these 4 boxes. And that makes a plus sign or a cross in between what I've drawn, which puts it in the negative space. That doesn't mean it's not there. That just means it's only illustrated by its lack of illustration. So we can say that the cross shape or the plus sign is visually represented by its lack of visual representation, or the borders of that which is visible are that by which we may catch a glimpse of the invisible. And I'm going to have a little beginner's guide to orthographic projection. You can see, here's a, can you see, can I zoom in? Yeah, okay. So we have the top, the side, and the front, and then that can be put together. That's orthographic projection, and then here's the plan view, which is the profile from the side, and the cross section, which is the face. And so you can see it looks different from the side than it does from the face. You put the two together to create a solid 3D projection. Okay. So we have natural occurrences of helical forms, such as the Nautilus shell, the fern shoot, or galaxies themselves. But what is the most common, most fundamental example of a material formed in a helical shape? And that's right, of course, it's DNA. Wow, look, it's almost a perfect match for the orbital trajectory. So if we go back, see, this is the orbital trajectory, and it's going up and down and closer and further and around and around and around. And it's kind of like a strand of a double helix. So now, if we remember orthographic projection, we can take a cross-sectional plane of this double helix. Oh, look at that. If we assume that, well, we don't have to assume because we're looking at it. Remember, this is, on this graph, we've got a plane at the bottom. This is a projected plane, and this line isn't just up and down. This is a 2-dimensional projection of a 3-dimensional track, and you can see closer, further, further, closer, closer, further. So there's some room there, and that room is roughly circular. Hello, nature. Good to have you. And so we've got the yin and yang, which I thought was very interesting. And so if we look at the middle, the dividing line between the yin and the yang, then we have the plane of symmetry. We have the equal on one side, the opposite on the other, and the room in which it moves around. And so, any one piece of matter in the entire universe, remember, we're only tracking points, particles. As the universe moves through time or through space, whatever level of analysis we're applying to the material universe, it has a linear path forward through time here. And then we have the edges of the material universe, and then all the particles within it, any one of them, just for simplicity of analysis, will loop around the track and do the same thing that we were looking at before. There's less on top, puts tension on it. There's more on the bottom, it wiggles. So that implies, with the concept of negative space and Newton's third law of motion, it implies the existence of an equal and opposite reaction to our universe. So that suggests the existence of a mirror universe. And here's the plane of symmetry. So remember, this is the plan view, and here's the universe, and here's the mirror universe, the equal and opposite. Here's a plane of symmetry, the extent of the curvature, and this is the cross section of it. I should have put it both on the same slide. But yeah, that's the mirror universe. And that's what we're talking today. And I only got 12 minutes into the stream, and I've pretty much summed the whole thing up. Any questions? Other than how many viewers I would like. Any questions from real people, not bots? And we'll go through it again. So we start on Earth, and we track a place on Earth. This path, the straight path, is Earth's orbit, and then tracking the point on Earth, it moves around the Earth, around the path of orbit, over time. And if we track the Earth and the Sun and the place on the Earth spins around Earth's orbit, but Earth's orbit spins around the Sun. And at the center of our galaxy, presumably there's a supermassive black hole, as we understand it to be. And we have the Sun, the Earth, and the place on Earth, and it's all doing the exact same thing. And of course, there's like, if you track every piece on Earth, you end up with this more, or this. And this is just a cloud of points that are all spinning around each other. And as it moves through space, it comes closer, it goes further, closer down, further up, further down, closer up, closer down, and further up. Tracking a waveform. Even though it's a particle. And the question is, how does light function, or how do things other than light function as both a wave and a particle as observed in quantum experiments? Like experimentation of quantum mechanics. And I think this is how. It's just a matter of scale, which the quantum theory studying scientists, the scientists studying quantum theory, know full well that it's just a matter of scale. In theory, the double slit experiment, if you're familiar with the double slit experiment, it's... hang on. Can I bring this up? Add source, window capture. What? No. Why is streaming gonna be so tricky? I should have set this up earlier. So in modern physics, the double slit experiment demonstrates that light and matter can exhibit behavior associated with both classical particles and classical waves. This type of experiment first described by Thomas Young in 1801, making his case for the wave behavior of visible light. In 1927, Davison and Germer, and independently George Paget Thompson and his research student Alexander Reid demonstrated that electrons show the same behavior, which was later extended to atoms and molecules. Where is it going to say? In the basic version of this experiment, a coherent light source, such as a laser beam, illuminates a plate pierced by two parallel slits, and the light passing through the slits is observed on a screen behind the plate. The wave nature of light causes the light waves passing through the two slits to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles. However, if the light is always found to be absorbed at the screen at discrete points as individual particles, not waves, the interference pattern appears via the varying density of these particles hits on the screen. Furthermore, versions of the experiment that include detectors at the slits find that each detected photon passes through one slit, as would a classical particle, and not through both slits, as would a wave. However, such experiments demonstrate that particles do not form the interference pattern if one detects which slit they pass through. These results demonstrate the principle of wave-particle duality. Now, is it gonna variations of the experiment, final result? Ooh, this is interesting. Huh. Single particle detection. Oh man. Okay, it restarted, which states that all matter exhibits both wave and particle properties. The particle is measured as a single pulse. Max and we are extending far beyond my understanding of quantum theory. The Mach-Zehnder interferometer, sorry, I'm learning here, can be seen as a simplified version of the double-slit experiment. Instead of propagating through free space after the two slits and hitting any position in an extended screen, the interferometer, the photons can only propagate in the interferometer, the photons can only propagate via two paths and hit two discrete photodetectors. This makes it possible to describe it via simple linear algebra in dimension 2 rather than differential equations. I hated differential equations, man. That was when I made it into mathematics, and I was like, you have to know the answer to make the equation. I don't see the point. I'm sure there is a point. It's just that my high school math teacher could not teach it to me. They were incapable of describing to me what the point of a differential equation was, and so I just didn't care. A photon emitted by the laser hits the first beam splitter and is then in a superposition between the two possible paths. Yes, okay. And in the second beam splitter, these paths interfere, causing the photon to hit the photodetector on the right with probability 1. Down just a wee bit more. And the photodetector on the bottom with probability 0. Huh. Hits the first beam splitter. Okay, right, okay. And blocking one of the paths, or equivalently detecting the presence of a photon on a path, eliminates interference between the paths. Both photodetectors will be hit with. Oh, I didn't change my. It still says Casual Fridays. It's not Friday. Currently, keyframes are not being. Keyframe frequency of 4 seconds or less. I don't even know what that means. Okay, the title was changed. That was all visible. I'm so bad at streaming. Okay, so back to quantum theory. Blocking one of the paths, or equivalently detecting the presence of a photon on a path, eliminates interference between the paths. Indicates that after the first beam splitter, the photon does not take one path or another, but rather exists in a quantum superposition of the two paths, which way experiments on the principle of complementarity. A well-known thought experiment predicts that if particle detectors are positioned at the slit, this is a thought experiment showing through which slit a photon goes, the interference pattern will disappear. This which-way experiment illustrates the complementarity principle that photons can behave as either particles or waves, but cannot be observed as both at the same time. Despite the importance of this thought experiment in the history of quantum mechanics, for example, see a discussion on Einstein's version of this experiment, we will. Technically feasible realizations of this experiment were not proposed until the 1970s. Naive implementations of the textbook thought experiment are not possible because photons cannot be detected without absorbing the photon. That always gave me pause. Currently, multiple experiments have been performed illustrating various aspects of complementarity. An experiment performed in 1987 produced results that demonstrated that partial information could be obtained regarding which path a particle had taken without destroying the interference altogether. This wave-particle trade-off takes the form of an inequality relating the visibility of the interference pattern and the distinguishability of the which-way paths. Is this a Bohr-Einstein debate pre the quantum revolution? And their post-revolutionary debates were about making sense of the change. Erwin Schrödinger had redeveloped quantum theory in terms of wave mechanics formulation, leading to the Schrödinger equation. When Schrödinger sent a reprint of his new equation to Einstein, Einstein wrote back hailing his equation as a decisive advance of a true genius. In parallel, Werner Heisenberg's... Okay, then what is this? Partial differential equation. Huh. Wow, that kind of looks like... Oh, sorry, I just gotta get my windows out of the way. It kind of looks like this, huh? Wave packet. Huh. Each separate wave-only phase rotates as hyphenated, so that the time-dependent Fourier transform solution... Man, I am so far out of my depth. A well-known thought experiment... no, we read this. In parallel, Werner Heisenberg's Umdichtung paper reinterpreted old quantum theory in terms of matrix-like operators, removing the Newtonian elements of space and time from any underlying reality. Interesting. A year later, in 1926, Max Born, collaborating with Heisenberg, proposed that mechanics were to be understood as a probability without any causal explanation. Both Einstein and Schrödinger rejected Born's interpretation with its renunciation of causality, which had been a key feature of science till present in general relativity. Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. Theory says a lot, but does not really bring us any closer to the secret of the, quote, old one, end quote. I, at any rate, am convinced that God is not playing at dice. At first, even Heisenberg had heated disputes with Bohr about whether his matrix mechanics were compatible with Schrödinger's wave mechanics. Okay. Please tell me there's an illustration. There doesn't appear to be an illustration. The Schrödinger picture? Can you not show me the Schrödinger picture? Okay, there is no actual picture. That's a shame. Okay, I did not take enough maths to really understand what I'm looking at here. Matrix mechanics is a formulation of quantum mechanics created by Werner Heisenberg, Max Born, and Pascal Jordan in 1925. First conceptually autonomous and logically consistent formulation of quantum mechanics. Its account of quantum jumps supplanted the Bohr model's electron orbits. It did so by interpreting the physical properties of particles as matrices that evolve in time. Oh, wait, you can't. Why can't you see? So this is what I was just looking at. Wait, no, Not like that. Not like that either. Okay, this is better. The fields indicate the probability of an electron being found in a particular location around the nucleus of the hydrogen particle at any given time, given by the color. Okay, yeah, so it's most likely to be where the light is. Probability density plots. Okay, now I didn't take enough physics to really understand what I'm looking at here. Should have taken more physics. Matrix mechanics. In some contrast to the wave formulation, it produces spectra of mostly energy operators by purely algebraic or ladder operator methods. Yeah, okay. Relying on these methods, Wolfgang Pauli derived the hydrogen atom spectrum in 1926 before the development of wave mechanics. Before the development of wave... Huh. Well done. Formulated the matrix representation of quantum mechanics, Epiphany Heligoland. 1925, Werner Heisenberg was working in I don't know how to pronounce that, on the problem of calculating the spectral lines of hydrogen. By May 1925, he began trying to describe atomic systems by observables only. On June 7th, after weeks of failing to alleviate his hay fever with aspirin and cocaine, damn, you'd think that would work, huh? Heisenberg left for the pollen-free North Sea instead of Heligoland. While there, in between climbing and memorizing poems from Goethe, West or Clicker Dewan, he continued to ponder the spectral issue and eventually realized that adopting non-commuting observables might solve the problem. He later wrote, "It was about 3 o'clock at night when the final result of the calculation lay before me. At first, I was deeply shaken. I was so excited that I could not think of sleep, so I left the house and awaited the sunrise on the top of a rock." Man, scientists used to be so fucking cool. Like, physicists, right? After Heisenberg returned to Göttingen, he showed Wolfgang Pauli his calculations, commenting at one point, "Everything is still vague and unclear to me, but it seems as if the electrons will no more move on orbits." On July 9th, Heisenberg gave the same paper of his calculations to Max Born, saying that he had written a crazy paper and did not dare to send it in for publication, and that Born should read it and advise him prior to publication. End quote, prior to publication. Heisenberg then departed for a while, leaving Born to analyze the paper. In the paper, Heisenberg formulated quantum theory without sharply defined electron orbits, directly advocating for a reinterpretation of quantum theory that only focused on experimental observables like frequency and transition probabilities. For Heisenberg's paper, Kramers had calculated the relative intensities of spectral lines in the Sommerfeld model. Okay, interpreting the Fourier coefficients of the orbits as intensities, but his answer, like all the calculations in the old quantum theory, was only correct for large orbits. Interesting. I'm sorry, I'm learning so much today. I wish I had... Yeah, there you go. Now you can actually see the whole window. And I definitely... It was about 3 o'clock at night when the final result of the calculation lay before me. At first, I was deeply shaken. I was so excited that I could not think of sleep, so I left the house and awaited the sunrise on the top of a rock. Amazing. Absolutely amazing. Heisenberg, after a collaboration with Kramers, began to believe that transition probabilities describing quantum transitions would need a new interpretation different from classical mechanics, because Heisenberg believed that the frequencies that should appear in a series describing the position of the electron should only be the ones that are experimentally observed in quantum transitions, like through spectral lines, not the complete set of spatial frequencies that come from making a traditional Fourier series of classical quantities. In Heisenberg's original formulation involved a series that described position as a series of virtual oscillators with 2 indices, with the two indices representing the initial and final states of a quantum transition. Rather than following the multiplication rule as expected from multiplying Fourier series, Heisenberg formed a non-commutative multiplication rule to ensure that multiplying position states would preserve the frequencies that are only found in the quantum transitions. I'm losing it. When Born read the paper, he recognized the formulation, particularly the non-commutative multiplication rule, as one which could be transcribed and extended to the systematic language of matrices, which he had learned from his study under Jacob Razans at Brillau University. Born, with the help of his assistant and former student Pascal Jordan, began immediately to make the transcription and extension, and they submitted their results for publication. The paper was received for publication just 60 days after Heisenberg's paper. Neat. A follow-on paper was submitted for publication before the end of the year by all three authors. A brief review of Born's role in the development of the matrix. Along with the discussion. This is all in parentheses. Okay, great. A whole paragraph for this one sentence, and then all of these parentheses. That's crazy. Up until this time, matrices were seldom used by physicists. They were considered to belong to the realm of pure mathematics. Interesting. Thus requiring Born and Jordan's paper to introduce matrix algebra to physicists unaware of their use. Gustav Mie had used them in a paper on electrodynamics in 1912, and Born had used them in his work on the lattices theory of crystals in 1921. While matrices were used in these cases, the algebra of matrices with their multiplication did not enter the picture as they did in the matrix formulation of quantum mechanics. Born, however, had learned matrix algebra from Razans, as already noted, but Born had also learned Hilbert's theory of integral equations in quadratic forms for an infinite number of variables, as was apparent from a citation by Born of Hilbert's work in German, published in 1912. Jordan, too, was well equipped for the task. For a number of years, he'd been an assistant to Richard Caron. Okay, background. John von Neumann became assistant to David Hilbert. He would coin the term Hilbert space to describe the algebra and analysis which were used in the development of quantum mechanics. A linchpin contribution to this formulation was achieved in Dirac's reinterpretation synthesis paper in 1925, which invented the language and framework usually employed today, in full display of the non-commutative structure of the entire construction. Oh, sorry, hell of a yawn. Before matrix mechanics, the old quantum theory described the motion of a particle by a classical orbit with well-defined position and momentum, xt pt, with a restriction that the time integral over one period t of the momentum times the velocity must be a positive integer multiple of the Planck constant as described by the sum of forces. Yeah, I mean, fair enough. While this restriction correctly selects orbits with the right energy values En, the old quantum formalism did not describe time-dependent processes such as the emission or absorption of radiation. When a classical particle is weakly coupled to a radiation field so that the radiative damping could be neglected, it will emit radiation in a pattern that repeats itself every orbital period. Really? Classical particle. Okay. The frequencies that make up the outgoing wave are then integer multiples of the orbital frequency, and this is a reflection of the fact that xt is periodic, so that its Fourier representation as frequency is 2 pi n over t only. The coefficients xn are complex numbers. The ones with negative frequencies must be the complex conjugates of the ones with positive frequencies, so that xt will always be real, as opposed to an irrational number. A quantum mechanical particle, on the other hand, cannot emit radiation continuously. It can only emit photons. But under the Bohr model, for a quantum particle starting in quantum number n that then emits a photon by transitioning to orbit number m, the energy of the photon is En minus Em. That gives a photon of frequency is the energy of the photon that gives the photon of frequency is En minus Em over h. In the formula above, t is the classical period of either orbit n or orbit m, since the difference between them is higher order in h. Oh, I missed a bit. For large n and m, but with n minus m relatively small, Bohr's correspondence principle expects the same classical frequencies. En minus em is roughly equal to hn minus m over t. In the formula above, t is the classical period of either orbit n or orbit m, since the difference between them is higher order in h. But for small n and m, or if n minus m is large, the frequencies are not integer multiples of any single frequency. Since in classical mechanics, the frequencies that the particle emits are the same as the frequencies in the Fourier description of its motion, Heisenberg inferred that in the time-dependent description of the particle, there should be something oscillating with frequency n minus m over h. Heisenberg called this quantity x n m and demanded it should reduce to the classical Fourier coefficients in the classical limit. For large values of n and m, but with n minus m relatively small, x n m is the n minus mth Fourier coefficient of the classical motion at orbit n. Since x n m has opposite frequency to x m n, the condition that x is real becomes, okay, by definition, x n m only has a frequency, so it's time evolution, so it's maybe described as t is energy to the power of I 2 pi factor en minus em t over h x n m parentheses 0. Huh. Okay, this is the original form of Heisenberg's equation of motion. Given two arrays x and m and p and m describing two physical quantities, when modeling each as classical Fourier series, it is expected that their multiplication x n k p k m should also result in a new frequency as part of a new Fourier series. Whilst the Fourier, I'm pronouncing this incorrectly, coefficients of the product of two quantities is the convolution of the Fourier coefficients of each one separately, Heisenberg changed the multiplication rule to ensure that when multiplying the new frequencies would only correspond to frequencies that already existed in the quantum orbit. Born noticed that this is the law of matrix multiplication. Oh, okay, obviously. So that the position, the momentum, the energy, all the observable quantities in the theory are interpreted as matrices. All the observable quantities. Okay. Under this multiplication rule, the product depends on the order. xp is different from px. Okay. The X matrix is a complete description of the motion of a quantum mechanical particle. Because the frequencies in the quantum motion are not multiples of a common frequency, the matrix elements cannot be interpreted as the Fourier coefficients of a sharp classical trajectory. No, they can't. That bit I actually kind of did understand. Nevertheless, as matrices, xt and pt satisfy the classical equations of motion. Also see Ehrenfest's theorem below. Matrix basics. Oh, wonderful, we're getting to the basics. When it was introduced in Werner Heisenberg, Max Born, and Pascal, okay, when it was introduced in 1925, matrix mechanics was not immediately accepted and was a source of controversy at first. Schrödinger's later introduction of wave mechanics was greatly favored. Wave mechanics, where did we get? Partial wave function. Obviously, preliminaries. Oh, it's this guy. Okay. Neat. Part of the reason that Heisenberg's formulation was in an odd mathematical language for the time, or Schrödinger's formulation was based on familiar wave equations, but there was also a deeper sociological reason. Quantum mechanics had been developing by two paths, one led by Einstein, who emphasized the wave-particle duality he proposed for photons, and the other led by Bohr that emphasized the discrete energy states and quantum jumps that Bohr discovered. De Broglie had reduced the discrete energy states within Einstein's framework. The quantum condition is the standing wave condition, and this gave hope to those in the Einstein school that all the discrete aspects of quantum mechanics would be subsumed into a continuous wave mechanics. Matrix mechanics, on the other hand, came from the Bohr school, which was concerned with discrete energy states and quantum jumps. Bohr's followers did not appreciate physical models that pictured electrons as waves, or as anything at all. They preferred to focus on the quantities that were directly connected to experiments. I can appreciate that. In atomic physics, spectroscopy gave observational data on atomic transitions arising from the interactions of atoms with light quanta. The Bohr school required that only those quantities that were in principle measurable by spectroscopy should appear in the theory. In principle, okay. These quantities include the energy levels and their intensities, but they do not include the exact location of a particle in its Bohr orbit. It is very hard to imagine an experiment that could determine whether an electron in the ground state of a hydrogen atom is to the right or left of the nucleus. There was a deep conviction that such questions did not have an answer. Well, it's got to be somewhere, right? The matrix formulation was built on the premise that all physical observables are represented by matrices, whose elements are indexed by two different energy levels. The set of eigenvalues of the matrix were eventually understood to be the set of all possible values that the observable can have. Okay, since Heisenberg's matrices are Hermitian, the eigenvalues are real. Neat. If an observable is measured and the result is a certain eigenvalue, the corresponding eigenvector is the state of the system immediately after the measurement. Oh. The act of measurement in matrix mechanics collapses the state of the system. If one measures two observables simultaneously, the state of the system collapses to a common eigenvector of the two observables. If one measures two observables simultaneously, the state of the system collapses to a common vector of the two observables. Since most matrices don't have any eigenvectors in common, most observables can never be measured precisely at the same time. This is the uncertainty principle. I didn't know it was articulated that way. That's neat. If two matrices share their eigenvectors, they can be simultaneously diagonalized. In the basis where they are both diagonal, it is clear that their product does not depend on their order, because multiplication of diagonal matrices is just multiplication of numbers. The uncertainty principle, by contrast, is an expression of the fact that often two matrices A and B do not always commute, i.e. that AB minus BA does not necessarily equal 0. That's a really complicated one. If is there a... Okay. The fundamental commutation relation of matrix mechanics, epsilon k by x and k pkm minus p and k xkm equals I h dnm, implies that there are no states that simultaneously have a definite position and momentum. This principle of uncertainty holds for many other pairs of observables as well. For example, the energy does not commute with the position either, so it is impossible to precisely determine the position and energy of an electron in an atom. In 1928, Albert Einstein nominated Heisenberg, Born, and Jordan for the Nobel Prize in Physics. Was delayed until 1933. It was at that time that it was announced Heisenberg had won the prize in 1932 for the creation of quantum mechanics, the application of which has, inter alia, led to the discovery of the... Great, thanks Wikipedia. Led to the discovery of the allotropic forms of hydrogen, and Erwin Schrödinger and Paul Adrian Maurice Paul Adrien Maurice Dirac shared the 1933 prize for the discovery of new productive forms of atomic theory. It might well be asked why Born was not awarded the prize in 1932, along with Heisenberg and Bernstein proffers speculations on this matter. One of them relates to John joining the Nazi Party on May 1st, 1933, and becoming a stormtrooper. I never would have thought that I could get I was thinking of playing the Wikipedia game on this page earlier. I was like, how difficult would that be? But no, actually, it's a 2. And becoming a stormtrooper. Holy shit. Physicists were badass. No, okay, clarification. I don't think that Nazi stormtroopers are badasses. I'm saying fighting as a soldier is, in some regard, respectable, regardless of the ideology for which the soldier fights. Jordan's party affiliations and links to Born may well have affected Born's chance at a prize at the time. Oh, wait. Oh, wait. Is it Heisenberg had won? And Schrodinger and... Okay. I'm up with the point. Bernstein further notes that when Born finally won the prize in 1954, Jordan was still alive, while the prize was awarded for the statistical interpretation of quantum mechanics, attributable to Born alone. Heisenberg's reactions to Born for Heisenberg receiving the prize for 1932 and for Born are also instructive in evaluating whether Born should have shared the prize with Heisenberg. On November 25th, 1933, Born received a letter from Heisenberg in which he said he had been delayed in writing due to a, quote, bad conscience, end quote, that he alone had received the prize, quote, for work done in Göttingen in collaboration, you, Jordan, and I. Heisenberg went on to say that Born and Jordan's contribution to quantum mechanics cannot be changed by, quote, a wrong decision from the outside. So, a Nazi stormtrooper is partially responsible for our understanding of quantum mechanics. I didn't know that. I mean, it probably could have been deduced from information I was aware of, but in 1954, Heisenberg wrote an article honoring Max Planck for his insight in 1900. In the article, Heisenberg credited Born and Jordan for the final mathematical formulation of matrix mechanics, and Heisenberg went on to stress how great their contributions were to quantum mechanics, which were not, quote, adequately acknowledged in the public eye. Once Heisenberg introduced the matrices for X and P, he could find their matrix elements in special cases by guesswork. Source, I made it the fuck up, guided by the correspondence principle. Since the matrix elements are the quantum mechanical analogues of Fourier coefficients of the classical orbits, the simplest case is the harmonic oscillator, where the classical position of momentum xt and pt are sinusoidal. Clockwise orbits, huh. Jesus shit, we're not even halfway down the page. Further results. Wave mechanics. ABC. So ABC minus BCA equals ABC minus BAC plus BAC minus BC. Yeah, why wouldn't it? Oh, okay, that last bit's interesting. Allows the evaluation of the commutator of P with any power of X, and it implies that Pxn equals negative I n x n to the power of n minus 1. Huh. This is like, it's crazy that they even put this on Wikipedia. Like a regular person could understand what's going on here. I saw 3 dimensions. In particular, this means that a system of n interacting particles in 3 dimensions is described by one vector whose components in a basis where all the x are diagonal is a mathematical function of 3 n-dimensional space describing all their possible positions. Oh, effectively a much bigger collection of values than the mere collection of n 3-dimensional wave functions in one physical space. Schrödinger came to the same conclusion independently and eventually proved the equivalence of his own formalism to Heisenberg's. Great. Since the wave function is a property of the whole system, not of any one part, the GTJ-GFT. Okay, here we go. It's a new copy-paste. I didn't realize. Simplest 09. That's crazy that you use this account for outreach as well as Cloakly. And they're both 6-character combinations of varying letters. That's weird. Simplest 09. Sort your shit out. Now, where was I? The description in quantum mechanics is not entirely local. The description of several quantum particles has them correlated or entangled. This entanglement leads to strange correlations between distant particles which violate the classical Bell's inequality. Even if the particles can only be in just 2 positions, the wave function for n particles requires 2 to the power of n complex numbers. That's a lot. 1 for each total configuration of positions. This is exponentially many numbers in n, so simulating quantum mechanics on a computer requires exponential resources. Conversely, this suggests that it might be possible to find quantum systems of size n which physically compute the answers to problems which classically required 2 n bits to solve. This is the aspiration behind quantum computing, which I suggests that it might be possible. How much? Okay, we haven't read the correspondence principle. We're gonna have to look. How much money has been invested in quantum computing? 55 billion? $55 billion on something that might be possible. We don't even know. We have no idea. We're just like, well, it might be possible, so let's give it a go. Okay, we're about to end the stream, so let's go to the correspondence principle. This should be a lot simpler. A correspondence principle is in physics, is any one of several premises or assertions about the relationship between classical and quantum mechanics. The physicist Niels Bohr coined the term in 1920 during the early... Man, I'm losing my voice doing this shit. He used it to explain how quantized classical orbitals connect to quantum radiation. Modern sources often use the term for the idea that the behavior of systems, blah, 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 blah. Okay. Max Planck was the first to introduce the idea of quanta of energy while studying blackbody radiation in 1900. Bruh. And the start of the 20th century, in 1906, he was also the first to write that quantum theory should replicate classical mechanics at some limit, particularly if the Planck constant h, that's what h is, cool, were taken to be infinitesimal. With this idea, he showed that Planck's law for thermal radiation leads to the Rayleigh-Jeans law, the classical prediction valid for large wavelengths. Niels Bohr used a similar idea while developing his model of the atom. He provided the first postulates of what is now known as old quantum theory. Using these postulates, he obtained that for the hydrogen atom, the energy spectrum approaches the classical continuum for large n, a quantum number that encodes the energy of the orbit. Bohr coined the term correspondence principle during a lecture in 1920. Arnold Sommerfeld refined Bohr's theory, leading to the Bohr-Sommerfeld quantization condition. Sommerfeld referred to the correspondence principle as Bohr's magic wand. In 1921, appeared from two sources. Rose and Word. Okay, we've been going for over an hour. Not over an hour, just about an hour. And I am about to lose my voice. Classical limit of wave mechanics. The outstanding success. Okay, man, one more paragraph. The outstanding success of classical mechanics in the description of natural phenomena up to the 20th century means that quantum mechanics must do well in similar circumstances. Judged by the test of experience, the laws of classical physics have brilliantly justified themselves in all processes of motion. It must therefore be laid down as unconditionally necessary postulate that the new mechanics must in all these problems reach the same results as the classical mechanics. And I think that's the part they're having trouble with. First, the particle can be approximated by a wave packet, and the indefinite spread of the packet with time can be ignored. Paul Ehrenfest proves his namesake theorem that showed that Newton's laws of motion hold on average in quantum mechanics. Really? The quantum statistical expectation value of the position of momentum obey Newton's laws. Second, the individual particle view can be replaced with a statistical mixture of classical particles with a density matching the quantum probability density. This approach led to the concept of semi-classical physics, beginning with the development of WKB approximation used in descriptions of quantum tunneling, for example, in which one part of the system is described quantum mechanically, whereas the other is treated classically. Quantum tunneling, quantum mechanical phenomenon in which an object such as an electron or atom passes through a potential energy barrier that, according to classical mechanics, okay. Neat. All right. Well, we're going to leave it there. We went through my notes on the mirror universe, where I am not a physicist, I am not a mathematician, but I noticed that if you track the universe, it kind of makes it look like DNA, and that made me go, huh. And we investigated, bring it back up, double slit experiment, the Bohr-Einstein debates, matrix mechanics, which I largely did not understand, and correspondence theory, which is simple in premise but difficult in execution. The term generalized correspondence principle has been used in the study of the history of science to mean the reduction of a new scientific theory to an earlier scientific theory in appropriate circumstances. This requires that the new theory explain all the phenomena under circumstances which, yeah. Okay. Oh, right. Well, that all makes sense then. And so I think we're pretty much done. Thank you everyone who joined me. That's my ex. There we go. Back to the regular page. Oh, all the bot commentary. Yes, good to have you, bots. I mean, terrible to have you, but thanks for showing up anyway. I don't appreciate it. Thank you to Natchu, who showed up for a minute. And that's pretty much it. So I'm gonna go ahead and end stream. Have a great day.